Hi, this video is for the final project of MUSA 507 of University of Pennsylvania. The aim is to describe an app and its algorithm designed to predict heroin overdose and allocate so-called drug trucks for Cincinnati city public health officials. The city of Cincinnati experienced an unexpected spike in heroin overdose since 2016. So how to prevent this from happening again is an urgent problem. We can also see the overdose counts of the 3 years from the maps. Many patients take heroin as a painkiller, and this often leads to overdose. It's better to have drug providers near where they live. One solution is having drugs providing legal heroin or other alternatives, for example naloxone, for medical use. Just like food trucks, we call them drug trucks. Based on the risk-terrain model, the app evaluates where you need drug trucks and how many trucks are needed. The app has 4 feature functions. The first one is hotspot. It shows the current and past overdose hotspots. The user can also select year and month to get basic information of overdose responses. The second one is a risk map. It shows the places with overdose risk levels. The user can also select the range of different environmental factors to find the areas with corresponding risks. For each area selected, it shows the estimated overdose risk level. The third function suggests location for trucks in selected areas, and also the number of trucks. Higher risk relates to more or denser trucks. If the risk is too high, perhaps we need more than one truck in one location. So that's why the location numbers shown on the map are not always equal. The last function is route plan, which plans a route for each truck and estimates the distance from the starting point to destination. The user can choose starting point and the destination on maps, and the app will calculate the possible routes and distance. So, what is the decision-making process behind this app? The project is based on the assumption that heroin overdose is a function of exposure to its environments, including risk and predictive factors. Also, we assume that this happens relatively rarely and there may be latent overdose throughout the city. So we use Poisson regression to build the model and split the data into training and test sets. First, we validate it by time, which is 3 periods of different years. Then we split the areas of different incomes with the data as training and test sets, and compare the results from different sets. We split the city of Cincinnati into fishnet cells. The dependent variable is the count of overdoses in each cell from 2015 to 2018. And also we split it into 3 periods. That's for the future cross-validation. For the predictors, we have 3 types of them. The first is the count in each cell, including numbers of suicides and attempts, numbers of 311 requests, number of crime records for which we will write some priorities, and the number of vacant and foreclosed properties. The second one is the average distance to schools, hospitals, vacant houses, bus stops, and parks. And the third one is continuous variables, which are demographic patterns. After the Poisson regression, we put predictors all in the same scale. Therefore, we can get a better understanding of which variables play more important roles in predicting overdose. We tested the model across different times and areas of different incomes. The result shows that overdose is more problematic among poor communities. Our model describes the latent risk better than current densities. Now we have a robust model with good accuracy and generalizability when predicting overdose to help more patients in need.